So we are going to talk about a beautiful phenomenon, very interesting, very important, and that is called surface tension, which is related to mostly to liquids. Okay. Let's see some of the observations that we have. If we enter a tank or a bank of a river into the river, then we find that the water wets us but does not wet the ducts. Okay. We also see it's a phenomenon. We also see that the oil and water do not mix. Okay, oil stays at the bottom and the oil come up if the densities are different, but they don't mingle and they don't mix with each other. In lanterns and lamps, diyas, oil rises up a cotton wick in spite of gravity. Mercury does not wet glass, but water sticks to the glass. Water rises to the top of leaves of a tree. Again in spite of gravity, despite of gravity. All such and many other experiences, they are related to the free surfaces of liquids. Gases, they don't have a surface tension simply because they don't have any shape or any definite volume. But liquids have a definite volume but no definite shape. So when you pour the liquid into a container, there will be a free surface that will be there. It will acquire the free surface when put in containers, and these surfaces do possess some additional energy, and this additional energy and its study and how it is stretched, we say that the surface of a liquid is like a stretched membrane, etc. That is what we mean by the study of surface tension. To explain the surface tension, we see that the liquid stays together because of attraction between molecules. Attraction between molecules. Whether the molecules are well deep inside or whether they are at the surface. We can see I have just shown a particular molecule which is surrounded by several other molecules. These molecules may be having different energies, but the average energy of these molecules is the same. You can see that all these neighboring molecules inside the liquid, they attract this molecule under consideration. Okay. So inside the story is such that there is a net force of attraction, and that evolves a negative energy associated with this molecule. Okay. What does that mean? I'll explain to you a bit later. While on the surface, I've shown the molecule. There we have the molecules. There are no molecules above it. Okay, there are molecules on the side. If you have a molecule over here, then it will have molecules on the sides which will be attracting it, and therefore if it makes a membrane or a surface, it will be stretched kind of a thing, that will, okay. So there you can calculate and find out and display that there are attractive and repulsive forces, the balance of which I have just shown over here on the surface metal. Now, how do we say that there is some kind of negative energy associated with the molecule? Because when the molecules are possessed in a container like this, okay, and if we try to take these molecules apart and we have a process of evaporation, well, the molecules, they go long distances and make a gaseous mix where we have water molecules, for example. So to do so, I'm not talking about boiling, I'm talking about evaporation, where some energy is required to take the molecules apart from each other. If the evaporation takes place when a large amount of heat is supplied to the system, or the body of the liquid, it gains the energy from within the body itself. Of course, what we find, and you must have seen, that if you keep water in a bucket, and these are very hot days, even then, when you keep the bucket for a long time and you go and see, the bucket temperature falls and falls. So it becomes colder and colder. Why? Because the evaporation has taken place and the average kinetic energy of the molecules has gone down. Okay? So that is what defines the things. So molecules, if they have to be taken apart, that means you have to supply some energy to take them apart. The binding energy which they have between the molecules has to be provided to it, is to be looked after and provided to it so that the molecules go apart. Okay, so surface tension. What we do a very simple experiment where there is a film here between these two edges, and there is a bar which is free to slide. Okay. When we apply the forces, initially there is a balance so that there is equilibrium. Okay. Later on, if we increase the force here so that there is this film is stretched by a distance d, an extra distance, by manipulating the bar, then actually you see that the volume of the film is fixed. So by doing so, what we do is we create more surface, that is, the film is spread. To do so, it requires additional energy, and when the additional energy is given to the system, then the surface area increases. Okay. The work done on stretching is equal to, because this force is parallel to the displacement d, so F dot d is equal to Fd. This is stored in the film as an additional energy. Now, the extra area of the film is distance d multiplied to the length L. So dl on the upper side and dl on the lower side. The film has two surfaces, so the total extra area that the film has been stretched is dl plus dl is equal to 2dl. If the surface energy per unit area is S, then what happens? We can write 2dl into S as equal to Fd, this equation, which we obtained from here. So this gives us d and d cancel, and S is equal to F upon 2L. Of course, the unit is Newton per meter, which gives us the magnitude of the surface tension. Also, the S is also the surface energy per unit area of the liquid interface. Okay. So there we have an extra energy of molecules associated with the surface, the interface. And if on the surface I draw a free line over here, then this line is subjected to molecular attractions on either side. They are equal in magnitude and opposite in direction. So they are the line that we have just drawn arbitrarily is in equilibrium. This can be a line of molecules and this can be a line of atoms depending upon the thing. Okay. So equilibrium of the line is there due to the surface tension, and the surface tension is surface energy per unit area of liquid interface. This can be found with a very simple experiment where we have a surface brought in contact with the liquid, and then it is balanced by means of certain weights. But if you want to separate that and stretch it, then additional weights have to be put on the pan, maybe, and from there we can calculate as to what is the surface energy per unit area or the surface tension, which is an easy experiment. I leave it to you to do it all by yourself. So next we are going to talk about an extension of the surface tension, the same thing, and then naturally after dealing with some angles of contact, etc., we will delve into what is known as the capillary rise and tell you many interesting things about it. Thank you very much.